So this chapter is about high availability. We are going to discuss about high availability on Nexus 7K. High availability means what? When anytime it is available, even if something crashes. That's what high availability. So our understanding for today is in what way Cisco Nexus 7000 is highly available, how it is redundant, what all the ways redundancy can be seen. Now, if you talk about redundancy, the entire 7000 or the entire classes that we are going to have on 7000 is about network redundancy, network high availability. But in this class, we're especially going to focus on system high availability, the physical box high availability. The network high availability will definitely come to that. When you talk about VPC, what we do is high availability. When we talk about FabricPath, high availability. When we talk about VDC, high availability. They are all network high availabilities. But does the system itself has high availability or not? That's what. Like, when we fly on an aeroplane, we trust even if one engine fails, there is other two engine or other three engines to carry us safe down to the ground. High availability. System high availability. That is system high availability. So likewise, the Nexus, do we have high availability? Yes, we do have high availability. This chapter is about that high availability. Now, before getting into again system high availability, I would also brief you a small introduction on network level of high availability. And then we'll get into system level of high availability in detail. A little introduction to network level, high availability, and then system level high availability will go in detail. And then in system high availability, we have very detailed study about ISSU. In service software upgradation, ISSU, in service software upgradation that can be performed on a Cisco Nexus without interrupting data plane, without interrupting the data flow. We can do upgradation. That's what in service software upgradation. So these are the three main objectives of today's class. Now, if you see the network availability, high availability, we already have layer 2, layer 3, layer 2.5 high availabilities. Example, STP. This is not talking exactly about only 7000 or Nexus. It generally talks about high availability networking. STP is a layer 2 high availability. In a normal switch itself, we have STP, which will pick one active link, all the others will be standby. If the active link goes down, one of the standby will become active. That is what high availability. And we have BPDU guard, root guard, loop guard, bridge, BPD filter, bridge assurance. What is these things? These things also provide high availability. How? When you guard a port from a BPDU, which means you do not expect BPDU on that port. So if an attacker comes with a BPDU, then the port goes to inconsistency state. What it is? High availability. It makes sure that attacker will not take over our device. It makes sure that BPDU makes sure that we got protected. We got highly available device. It's not going to get compromised and lost because of some attacks. Likewise, loop guard, preventing from loop, root guard, preventing some switch to become a root. It prevents any switch becoming a root switch. It allows only the switch that we want to be a root switch to be a root switch. Likewise, BPD filter, bridge assurance, all these things are what high availability concept. UDLD is also again hardware level high availability concept. What is that? Even if STP fails to prevent loop, UDLD will kickstart and stop the loop. Unidirectional link detection. This UDLD is small protocol that keeps pinging, that keeps sending a kind of hello packets on the link. When it detects some hello packet mismatch or something like that, some hello packet is missing, then it identifies that there is some disconnection. But if there is a loop and hello packets are getting, if STP didn't detect loop, if hello packets are still coming, then there is a loop, UDLD will go and block it. These are all routing and switching world anyway. Now VPC is our Nexus solution. Port channel is there before Nexus itself. Now we have port channel bundling of link, but the drawback of port channel is what? We cannot bundle links that goes to multiple upstream switch. Port channel is links bundled between two switches, one upstream, one downstream. Whereas VPC is bundling links that goes to multiple upstream switch, which we already have an idea what is VPC. We already had some class on VPC. FabricPath. FabricPath is like we have servers on two sides. In the middle we have a lot of layer 2, and we don't want that layer 2 to undergo STP. So what we do, we do FabricPath, where switches will be using ISIS protocol behind the screen to find the shortest path to reach the server on the other end. For this, there should be an enhanced license. It's not freely available in Cisco Nexus. We can also use 120 days free license to test this. Likewise, we have HSRP, VRRP, GLBP for layer 2, layer 3, first hop redundancy protocol for redundancy, and we also have bidirectional forwarding to detect a link failure. In OSPF, both in IPv4 and IPv6 OSPF, and in EIGRP, in ISIS, and BGP, in all this protocol we have something called graceful restart. What is that? High availability. What is graceful restart? I'm going to do some changes in my router. Let me think myself as BGP. I want to do some attribute change. So what I do, I send a reset message to my neighbors. Neighbors, wait, I'm there. Don't assume I'm dead. I'm there, but I'm changing my policy. And I reset the connection. I re-establish the connection. I send fresh updates to my neighbor. So these are all what? High availability. Likewise, we have high availability everywhere. Some are free, some are only through some special license. The next chapter that we are going to see is about VDC. VDC is also high availability. How? We have VDCs means what? Virtual device context, meaning we have a lot of virtual device on a single hardware, one nexus acting like 4 nexus switches. How high availability is there? Yes, there is high availability. Now, because these VDCs are independent of each other, they don't depend on each other, they don't talk, they are completely a separate device, but it's a virtual device. A failure on one VDC or a process failure on one VDC, like let's say OSPF fails on one VDC, that is not going to affect the OSPF on the other VDC. So what we see here is high availability. So each VDC runs separate STP instance, first hop resolution protocol like HSRP or VRRP or GLBP got separate routing table. So they are independent. They are totally complete. They don't depend on other VDCs. So failure in other VDC is not going to affect anything here. So there is high availability. So this explains the difference between port channel and virtual port channel. Virtual port channel is between aggregation of links between two switches, whereas VPC, virtual port channel, is between normal port channel is between two switches, whereas virtual port channel is between three switches. Upstream switches, two switches are called as VPC peers. According to the downstream switch, the upstream two switches are considered as one switch. They are grouped logically as one switch. So you can have still VPC port channel, we can have still port channel, though we are connected to two different upstream, still we can have port channel without any link having a block or alternate port. All links will be active, and here we get more throughput than here. Same Cisco FabricPath, it's again layer 2 layer 2 routing, I can say, and it is layer 2 load balancing technique, where we have a lot of layer 2 device in which we have enabled FabricPath, and it uses ISIS to find the shortest path to reach the other end where the server is connected. It can also take multiple paths depending on the availability. So it uses switch ID to identify the device inside the FabricPath. Anyway, we have a very separate, unique chapter about. We have a dedicated chapter about FabricPath coming later. So this is just to introduce you that there is high availability in both network as well as the system. HSRP is also high availability solution, where we have a floating IP address as a gateway. If one of the active device goes down, standby device will have the floating IP address, and we have redundancy, we have high availability. We are not going deep into HSRP. If needed, means if you want really HSRP, then we'll cover it in a separate class. It's a routing and switching topic. Now when we have STP as well as HSRP, there is a problem, because STP has blocking ports. It needs to always take a long route. It cannot, this switch cannot talk to this switch like this. It has to take always a long route, and one of the link is blocking, so you are not efficiently using all the bandwidth. So to avoid this problem, we have VPC. Still you can have HSRP, one active switch, one standby switch. All links are available for us. HSRP also can be used for load balancing. How? I can have multiple HSRP group ID groups. Group 1 will be active here and standby on this box, and group 2 will be active here and standby on this. So HSRP can do load balancing. Now VRRP is also same like HSRP, but one difference is, for HSRP you need a special dedicated floating IP address. For VRRP you can have special dedicated IP address, or we can use one of the physical interface from this switches, one of the physical interface IP address as the floating IP address. Timers are here 3 and 10 in HSRP. In VRRP it's 1 and 3, but still HSRP timers can be tuned even in millisecond. VRRP timing can also be tuned. So this shows the difference between HSRP and VRRP. Well, one point is missing here, that is HSRP we have active standby, in VRRP we have master backup. That word is missing. But other than that, all other things are mentioned here very clearly. Alright, GLBP is again same like HSRP, the timers are same, but one difference is we need not to run multiple we need not to run multiple GLBP in order to have load balancing. Just have one GLBP, load balancing will happen. Both the devices will be in use. So GLBP is much advanced than HSRP. The differences we see here. These things are not that important for us, but still we have HSRP configuration on Nexus device in exam. But that is very easy. We need to just put in some priority, preemption, and the floating IP address. So we have a separate chapter on HSRP along with Nexus coming later. So need not to worry even if you don't have much clear understanding about these topics. These are all routing and switching topics, but still it is coming here also. Because it is there for exam, we have a separate chapter on it. This shows how the GLBP works. There is something called AVG, Active Virtual Gateway, and AVF, Active Virtual Forwarder. Active Virtual Gateway takes care of the sharing of MAC address between multiple clients. So one client will be using the MAC address, virtual MAC address of this device. Another client will be having the MAC. Other client will be having the MAC address of this virtual device. So what happens is, because the MAC address layer 2 address are separate, but layer 3 address is same. Though layer 2 address is separate, it will go to this. One device will go via this. Another device will go via this. So we can also have GLBP with VPC without any problem. Only in normal STB, because of the block, there is a problem. So that's why we are going to learn about VPC later, not now. It shows the difference between our traditional layer 2 high availability and today's Nexus based high availability. It shows the difference between these two. BFD is the one which sends hellos every often on the physical links to identify the link failure. If the link failure happens before the routing protocol detects, BFD will detect the link failure and inform the routing protocol to immediately switch over to the another path. That's the job of BFD. BFD can work with any routing protocol like BGP, RIP, except RIP, BGP, OSPF, EIGRP, ISS, and so on. Now Cisco Nexus has got not only Cisco Nexus, this is in general, this example is common, not only for Nexus. If OSPF wants to if OSPF wants to do some sort of reset, like I say clear IP OSPF process. So OSPF is getting reset. So what it does before the reset starts, it sends a graceful reset message, restart message to the neighbor, so that the neighbors will send the routing update from their database. So this OSPF need not to send a hello packet and discover the neighbors and then get synced. That is not needed. When a graceful reset is restart is sent to the neighbors will automatically send the update. It can synchronize as early as possible without disturbing the data plane, the data stream that is going on the data plane. Still the data is flowing, though OSPF is getting its route updated, the change happening. Layer 2 is not getting disturbed, it just keep on going uninterruptedly. So this is again another high availability. This is called non-stop forwarding. The data plane is not getting stopped because of the change in control plane. So this is again one high availability example. Right, from here starts the system redundancy, which is our focus for the day. System redundancy. Now, supervisor module, if you see, in Nexus, it's not like router. In router, if I want to do some upgradation, the entire device will be in a down state for a while. If I want to reload, I need to reload the entire device. I cannot reload only the control plane, because the normal switches and routers are not modular based, whereas Nexus is modular based. We have all our IOs or the data planes in a separate module, and we have supervisor module separate. And if I want to do some change, I can do only to this and I can restart this without affecting this. Modular based. So we got two supervisor now, not only one, just one. We have got two. It can also run with one, but we got two supervisor module. Why we have two supervisor module? Where we will make one as active and one as standby, and if needed we can do upgradation like in service software upgradation, which we are going to see at last. We can do that on one standby device, as the active is already controlling this data plane. We can do the upgradation on standby device, and then once the upgradation is done, switch over, make this updated standby as active, and go to the original active device, active supervisor engine, and do the upgradation. And if necessary, if you want to go back to active here, we can do that. So kind of upgradation is made simple without downtime, plus high availability, meaning if one supervisor engine goes down, still you got another supervisor engine to control the data plane. High availability. So having dual supervisor engine, supervisor module is good. 1+1. We got redundancy for control and management plane. So everything is module. IO is separate module, supervisor engine is separate module. Cisco switch fabric. As we all know that Nexus device have got lot of IO ports on the front panel. To control the traffic between these IO ports, behind on the rear side we have lot of fabric modules. It is this fabric module which controls the traffic flow in this IO ports and this data plane. So these fabric modules are also redundant. If one of the fabric module goes down, traffic will not get affected. All the traffic that was going through this fabric module will be shared between the other. So the failure of the switch fabric module triggers an automatic reallocation and balancing of traffic across the remaining active fabric modules. So there is high availability. Power supply. We got some 7010 series has got 3 power supply modules. With the 3 power supply module, we can have 4 different different types of redundancy, high availability. We'll talk about that. And in 718 series we got 4 power supply. Now each power supply will have 2 separate power inputs totally independent of each other, meaning I'll show in the diagram. Yeah. So like this we got 3 for 710. If you see, each has got 2 inputs. This and this are totally independent. This is connected to every module. This is also connected to every module. So I can take one power source and connect here, maybe from my generator 1. I'll connect this one from generator 2. If generator 1 fails also, I will not go down, because generator 2 is providing supply. So if I say 3 power source, actually it is 6, because we got 2 to each. 3 means it is actually 6 ports, 6 power inputs. Fan trays, we got 1 extra always. For IO module cooling we need actually 1, but we got 2. For fabric modules we got 2, actually we need 1. So if one fails, we are not in trouble, the other one is there. But the only thing is, if I have 2 modules of fan, if this is failing, I should not remove this module because it is failed. I need to keep it installed there. If I remove this, what will happen? The inside cooling system will get disturbed. So we should remove this module only when you are ready to replace with a new module. Otherwise we need to leave this crap in there to maintain the cooling. So that is the condition. So there is redundancy in supervisor engine, there is redundancy in fabric module, there is redundancy in power supply, there is redundancy in fan. Right. So this talks about dual supervisor engine, how they work. Yes, sir. Correct. This is 7,000, right? So we got a dual supervisor module, 2 supervisor engines we got. Now how they work together. Now when active is controlling the data plane, standby, what it does is it sends a request for a snapshot. It sends a request to active device saying, what is your current position? What is your current status? That's what requesting for a snapshot. So active device says, this is the condition of my OSPF, copy it. This is the condition of my BGP, take it. My multicast is like this, take it. These are the things about this, take it. So an updation, a stateful switchover, a statefulness is maintained. Statefulness, that's what statefulness. Parallelly maintaining the changes. Any change that happens on active device is parallelly maintained on the standby device, which is facilitating a non-stop forwarding. How? If the active device goes down, standby device knows everything that was there on active device, all sessions, everything. So there won't be any downtime. It will be a non-stop forwarding. So this is why we need the snapshots and get synchronized simultaneously. So request is sent, snapshot is provided, and standby device synchronizes, and then it sends a notification, yes, I got synchronized, and then this sends the event driven message, okay, I'm happy you got synchronized, then I'll send you the next snapshot when you request. So a kind of acknowledgement. Yes, sir. You can also run in one supervisor engine. See. Mm. Yes, definitely. That is what Cisco will recommend because it's money for them, more money, and a supervisor module will not go down. It should not go down, but yeah, but you can have both. You can have two. You can have two, but it can also run on single. Mm. Mm-hmm. Mm-hmm. Okay. 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 So the memories are not getting refreshed. The mm. Mm-hmm. Mm-hmm. Okay. Okay. All right. So they are also slowly trying to rectify things. So how the supervisor switchover happens? See, even when we have multiple supervisor, switchover happens. What is switchover? Making standby is active happens in two different ways. One, manually. What is that? We go to this active device and say switch over. Then automatically standby will become active. There is another way that switchover will happen, that is automatic. When the active fails, that failure will trigger the standby to become an active. So there are two different ways a switchover can happen. Now, when the switchover happens both manually or automatic, one good news is non-disruptive. Stateful because control traffics are not affected. Already this standby device is updated because of statefulness. Standby device is up to date. Whatever was there information in this active device, it is there with standby. So when switchover happens, there is no real downtime at all. There is no downtime in data plane. Immediately standby is 100% equal, powerful, same like active device. Now there are only very less services that cannot be done statefulness. Only those services will be resynchronized. Most of the services are stateful and they are non-disruptive. So this will not disrupt the failover, switchover will not disrupt the traffic in the IO module. So only the supervisor module get reset, not the switching module. No reload of connectivity management. Okay, what is this? Connectivity management processor. This is a special port only on Soup Engine 1. It's a special port. It's a kind of Ethernet port on Super 1. What is the purpose of this CMP is? The CMP is like, we are in an aeroplane, we are flying. It should not happen, just I'm giving an example. All the engines failed. All the engines failed. Now, immediately what will happen? One fan will come down. Now, this is the aeroplane belly. When all the engines struck, when all the engines fail, this fan will come down. There will be a fan kind of. It's a generator actually. It will come down, and as it is flying on top, this will start rotating. As it rotates, it will generate a minimum power supply for the panel in the carpet to work. Because the engine failed, the dynamo stopped. So the panel will go black if this is not there. So this will come in the emergency. It will generate some power and give the power to the panel on the carpet plus the air condition for the passengers. Now, because these guys the pilots are seeing the panel, they can do some observation, and they can try to bring up the engines back as it is flying on the clouds, like this. CMP is like this fan. This has no contribution in flying the aeroplane, but this comes in picture only when this is totally not in control. When the aeroplane is totally not in control, this comes and gives a chance for us to take control of this aeroplane, this generator. Same like that CMP. CMP, what it does is it is totally out of band, meaning if these supervisors are not responding for you, you cannot take control over the Nexus box. But there is a chance to take control. CMP. If you try controlling the Nexus box through CMP port, you will be able to take control. Supervisor engines are struck, they are not supporting. Nothing is supporting for you to take over the device. It's malfunctioning, but CMP can allow you, CMP can provide you logs saying what's happening inside, why these devices are not responding, and CMP can help you to interact with the supervisor module or data module. CMP has its own processor, separate processor, its own separate small mini operating system. It is not depending on Nexus OS. It has got its own memory modules, RAM. It is totally out of band. So if something goes wrong, if Nexus device is not responding, you can interact through this port to the Nexus box. It is also a part of Nexus box, but out of band. They are not subjected to the Nexus iOS or a common processor and RAM. It has got separate control over this. So not only that, when you restart Nexus through CMP, you can see everything. The program all going down and program all coming up. So CMP is like every time watching. Even when the system restarts, there is someone watching this Nexus box. If our laptop goes down, after going down, we cannot really say what is happening inside. But CMP can say what is happening inside. And when it boots, it can say what is happening. It can show logs. That's what CMP is. So when we do switch over, there is no reload of CMP. That's what I said. This is a watchman always watching. Even during the switchover, this guy is opening his eye and seeing what is happening. We can say if something goes wrong during the switchover, we can clearly say through CMP what really went wrong, which will be easy for troubleshooting. That's what CMP is used here. Right. So okay. Now, before we do switch over, we need to keep something in mind. What is that? We need to check whether there is a standby device in a high availability state. Before switching over from active to standby, we need to check whether there is some standby to take over as an active. And we need to check whether we have all okay. Okay means all the IO modules are okay. All the IO modules should be okay. There should be another supervisor module to take over. It should be in HA standby, high availability standby. And then we need to check whether they have synchronized these boxes, active standby module. They are auto copied. They have done snapshotting, synchronization, statefulness. And then there may be some snapshot going on, copying going on. During that we should not do switchover. So we should make sure that there is no file currently being auto copied. All statefulness synchronization should get over. Only then I can do what? Switch over. So these are the things that we need to keep in mind. And then what we do is we say simply switch over. After switch over, see this box, this supervisor module 1, supervisor module 2. Supervisor module 1 I said switch over. Now supervisor module 2 will become, from standby it will become active. I need to wait for that. Once this has become active, what I can do is I can shut down this supervisor module and I can replace another supervisor module if I want to replace. So this is the procedure for replacing the supervisor module. First we saw how to do switchover. Once the switchover is happened, if you want to replace the supervisor module, wait till the switchover happens. Once the switchover is done, we cannot simply take it out. We should shut down properly. Out of service, if it is slot 1, supervisor is in slot 1, say slot 1. In the previous diagram, it is in module 1. Supervisor 1 is in module 1. So I say what? Out of service 1. When I say that, it is the proper shutting down. That's how we power down the supervisor, by giving this command. Out of service 1. And then we replace the module. After replacing the module, take the new module, reload module 1. If you say force, the reload happens immediately. If you don't say force, the newly added module will be loaded in 6 minutes. Who will reload it? The present active module will go and reload this newly added module in 6 minutes. If we don't say force, it won't happen immediately. The reloading will not happen immediately. It will happen in 6 minutes time. Automatically it will happen by the current active device. And then we need to copy all the snapshot, all the files from the current active device to the newly added standby device. We copy by giving this command. After we copy, we boot the newly added device with the copied file, and then we say copy run start so that it can be copied to the NVRAM permanently. So this is the replacement procedure and this is the switchover procedure. We'll stop here today and we'll continue from here tomorrow.